necessarily as familiar with it as stratospheric aerosol injection, as sort of setting the stage for the global modeling discussion that will follow. This is kind of the iconic image that you get with marine cloud brightening. These are ship tracks in the ocean. These are actually low clouds over the ocean where you have brightened streaks of clouds that can be traced back to cargo ship emissions. So this is where particulate pollution from the cargo ships are mixing into the clouds. And this is sort of a great iconic example of marine cloud brightening because you can see this effect visually. But it's actually an effect that's happening more broadly over the planet where pollution aerosols are mixing into clouds, but you just can't sort of see it visually where you have this more diffuse aerosol mixing into clouds and clouds are brightened. So with marine cloud brightening, the idea is that you would intentionally add sea salt aerosols to low clouds over the ocean in order to make them more reflective and cool climate that way. And I want to just emphasize on this that, so it's basically like the ship tracks, but more diffuse, ultimately, if you wanted to do it at a climate scale, and using sea salt instead of pollution. But I wanted to emphasize that with marine cloud brightening, you can't create clouds. You're taking clouds that exist and make them a little bit brighter, maybe a lot brighter occasionally, and sometimes maybe last longer and increase sunlight reflection that way. But you can't create clouds. So you can only do this in some locations. You have to do it at locations where there are clouds, specifically low marine clouds and specific types of low marine clouds. So your options for where you could implement MCB are more limited than with SAI. Now, of course, what we're ultimately interested in is how would marine cloud brightening affect not just global annual average temperatures, but climate, just like with SAI. How does it affect temperatures, precipitation, circulation patterns, all the climate impacts that follow from that? And as with SAI, the only way you can do that right now, understand that right now, is through global climate models. Otherwise, we would just be out there implementing it and seeing what happens. Unlike SAI, there's been pretty limited number of global modeling studies to date on marine cloud brightening, and most of them have been pretty unrealistic in a lot of different ways that I won't go into. But there will be, that's starting to change. You'll see presentations about some new model runs, and we're hoping to do an increasingly expansive number of runs, as have been done with SAI. So an issue with doing global model runs of marine cloud brightening is that the models struggle to represent some of the key processes that actually drive marine cloud brightening. An example here is, this is showing low marine cloud coverage using the same color scale in all the plots for 9 different climate models. So you can see that just, not even talking about marine cloud brightening, the models have a really hard time representing even just the presence in the cloud fraction for low marine clouds on the globe. So that's a challenge to represent marine cloud brightening when they can't even get the basic cloud cover right. A second issue is how they represent, is their representation of how the existing clouds then respond to the addition of aerosols. So the effect that we think of leveraging with marine cloud brightening, the original idea, is that if you take a cloud over the ocean where there usually aren't a lot of particles in the atmosphere, any water that condenses to form a cloud will condense on whatever particles exist there. There aren't many of them, so you get a small number of large droplets. With marine cloud brightening, or in ship tracks, or with any pollution aerosol mixing into these clouds, you now have more particles for that water to condense on. You end up with the water condensing over a larger number of droplets. You have a large number of small droplets. That basically increases the surface area of water in the clouds, and it's that surface area of water that reflects sunlight. And so it makes the cloud brighter. So that's the effect we think of when we think of marine cloud brightening. And we understand this process pretty well, and the models basically could do that pretty well. Although there are differences across global models in even that response. But where things get really, really complex is once the cloud has more smaller droplets, how does it then respond? You can imagine that cloud would be less likely to precipitate. And so it would retain its cloud water longer and reflect even more sunlight. But you can also imagine that it would evaporate more easily, particularly off the cloud top. And then you would lose cloud water, and that would offset the brightening from the droplets. Those things pull in opposite directions. How they play out depends on the conditions, really, really strongly on the conditions, and on processes that happen at really, really small scales. So the key processes driving these cloud responses cannot be resolved by global climate models. If you look at a global climate model, its resolution typically is sort of 50 to 100 kilometers on a side. If you just took like a quarter maybe of one of those boxes, that's what that domain would look like. You can see there's an enormous amount of complexity that occurs within a quarter of a global climate model grid box in the clouds. And so it can't directly represent these really critical processes to both how clouds form and how they respond to aerosols. And so the result is that across models you get really different responses. So this is just looking at two global climate models where you have a specified change in cloud droplets within three sort of grid box areas. In one of the models, that results in a response that those clouds then have a change in their water content, the amount of water in them, that's really large for model 2, but basically non-existent for model 1. Similar thing in terms of cloud fraction, really big response in model 2, not in model 1. So this is just showing those responses I was talking about play out really differently in different global models. Similarly, the amount of salt that it takes to produce a specific amount of cloud brightening varies enormously, just across 3 models by a factor of 10 in mass across 3 global climate models in order to produce the same amount of cloud brightness, because of a whole cascading set of things, but partly because of those differences in responses I was talking about. So these models really differ when you're talking about going from injecting sea salt to producing cloud brightening. So the key takeaways I want you to get from all of that, which was a little bit of a fire hose of information, is that you can't use global climate models to determine how much cloud brightening is possible, where it might be possible, and how much sea salt would be required to produce a certain amount of forcing from marine cloud brightening. But the global models are really, really useful for what they're built for, which is quantifying how would the climate respond to a given amount of cloud brightening in a given region for a given duration. So we can do things like, say, take a global model runs for a given greenhouse gas scenario, and if we impose the same amount of forcing in both of those models through marine cloud brightening, we can compare how they then respond, in this case to implementation of marine cloud brightening in 5 different grid boxes. So I want to step back a little bit. So that's sort of the liftoff point for the talks you're going to hear later in terms of what's being done with global modeling of climate responses to marine cloud brightening. I wanted to just really talk briefly about the other work that's going on, because there's a lot of the work with marine cloud brightening right now is not in the global modeling realm. It's in the realm of using observations and smaller scale, higher resolution models to understand these processes that the global models don't do as well. So this is another type of model called a large eddy simulation model. Covers a much smaller domain, about 25 by 25 kilometers. So again, about a quarter, a half of a global model grid box. And it resolves almost all of the complexity that you have in cloud fields, because of the higher resolution and more explicit representation of those processes. And we can use those models to simulate the injection of sea salt aerosol into low marine clouds. You can see in the top panel, this is the change in droplet density if you inject a single plume like you would in a ship track, how the amount of water in the cloud then responds in the middle panel, and then the change in albedo in the bottom panel. This is for one's very specific set of conditions. So we can do a whole lot of model runs like this under different conditions and see what the differences in response are under different conditions, and try and use that to better understand cloud responses to aerosols. Again, those are still models. They're better at representing this stuff, but they're still not perfect. So there's another area of work going on where we're hoping to be able to go out into the field and do field studies that would allow us to test those at a very small scale, that would allow us to test those high resolution models. And ultimately, the goal of all of that is to learn from this cloud scale modeling, observations, and field studies to get improved understanding of how the clouds respond to aerosols, and ultimately improve the global climate model representation of those processes.
Okay.
This is you.
So yeah, I'll hand it off to Matthew to discuss some recent global climate modeling.
Yeah, so I will introduce the new MCB protocol called G6 MCB 1.5K. So as Sarah nicely introduced, all of this work is in Earth system model world. So the scales are that we are looking at the global climate impact of MCB. And in preliminary work by Haruki, we looked at the impact of doing MCB in various areas. So the different columns are different models. And then the top row just shows how each model responds to an increase in greenhouse gases. The bottom row shows how each model responds to MCB in the tropics. And so we're basically seeding the clouds in each of these red boxes. And you can see that the cooling for tropical MCB is not very homogeneous, and even get warming in some areas. Then the middle row is the temperature response of doing MCB in the mid-latitudes, and you see that the temperature response is much more homogeneous. So you can look at the numbers, so the spatial correlation number. If it's closer to -1, it means it's similar to greenhouse gases. But if it's closer to 0, it means it's very different. So basically, tropical MCB gives a very inhomogeneous temperature change pattern, but mid-latitude MCB is really quite close to greenhouse gases. And so the strategy and scenario for G6 MCB 1.5K, so we decided to use those 5 mid-latitude regions. And we are using the same background scenario, so SSP 245, and the same global mean temperature target as the upcoming similar SAI scenario. So that is, we use a middle-of-the-road greenhouse gas emission scenario, and we're attempting to maintain global temperatures at 1.5 above pre-industrial temperatures. In order to do that, we have 2 preliminary simulations to do. So the first is what we call a fixed SST simulation. So that's an atmosphere-only simulation where the sea surface temperatures are fixed, and we do the emission of aerosols in these different regions. And that lets us, tells us how much forcing we are imposing on the model. So if we fix the sea surface temperatures and do the emission, you can look at the top of atmosphere radiation budget, and it basically tells us, yeah, how much forcing that gives. So we had to make some choices on how to do that exactly, like how much aerosol to emit in each of these boxes. We made the choice to have a hemispherically mass-balanced strategy, meaning that the total mass emitted in both hemispheres is the same across the 2 boxes in the northern hemisphere and the 3 boxes in the southern hemisphere. So we also thought about doing like a strategy where the forcing is balanced between both hemispheres, but we thought that it was unclear whether that was actually better, and overall it's like easier to implement and to interpret when you have a mass balance strategy. Anyway, so stage 2 is a coupled GCM simulation where we just do that constant emission for like 30 or 40 years, and that gives you the global temperature response for each of the models. So you see it doesn't like cool the planet straight away. There's a sort of a lag time. And so you can fit a curve through this temperature response. And you can then figure out the e-folding time. So basically, after each of these numbers of years, you get about half of the temperature response after those years. Which is actually quite interesting that if IMO 2020 is similar to mid-latitude MCB, then you can imagine actually it will take from like 5 to 15 years to get the total warming response from IMO 2020. So quite interesting. So yeah, and then the actual simulation that we ran is G6 MCB 1.5K. So again, we're attempting to maintain the temperature at 1.5K in each of the 2 models. So on the left is the UK model that I ran, and on the right is CESM2 that Haruki ran. The top plots are showing the total global emissions of sea salt aerosol in mass. And then the bottom plots are showing the temperature change, so for the greenhouse gas scenario in red, and then the MCB scenario in blue. So you can either do it manually, as I did, so basically the plot on the left. So for each decade, you sort of impose a constant emission. Or you can use a controller, which is kind of an algorithm that tells you how much to emit each year in order to maintain a certain temperature target, which is what Haruki did on the right. And so then, yeah, you can look at the temperature patterns for each of these simulations. So the top plot is basically showing you the response to the warming response from the greenhouse gas emission scenario. And then the middle row shows you the MCB temperature relative to the reference. And then the bottom row just shows you the MCB relative to SSP245 at the end of the simulation. And so as you can see, the cooling pattern is relatively uniform, which is quite interesting. And then, so we have more analysis to do on the precipitation pattern, but at least initial results don't suggest like large shifts in precipitation. We also, well, Haruki briefly looked at the potential for larger residuals when you look at the seasonal pattern, especially, for example, if you look at the top left. So basically, these are maps of the temperature response relative to the target, but for each season. So DJF is Northern Hemisphere winter, and then JJA is Northern Hemisphere summer. And so you can see there's some residuals there that I think there's more research to be done to really understand these. Yeah, and so it's quite cool because you can use these simulations to compare it to the similar simulations we did for SAI. So this G6 SAI 1.5K is the same temperature target and background greenhouse gas emission scenario. So again, the stuff in the maps in the middle are from MCB, and then the maps on the right are the same maps, but where we did SAI in order to get that same global temperature target. And so this is for the UK model, and this is for the CESM2. And what we found actually is it's remarkably similar. I really didn't expect that, because in my head, like, MCB is always supposed to, well, in my head, I always thought it would give quite a patchy cooling pattern. But it turns out if you do it in the mid-latitudes, well, it's remarkably similar to SAI, which I thought was quite interesting. So yeah, conclusions. We designed this new global climate modeling of MCB to be as close as possible to SAI. And the early results that we have suggest that quite reasonably homogeneous cooling and precipitation changes, though the seasonal residuals might be larger, so there's more research to do. And I'd just like to end with a plea to get in touch with us if you, would like to analyze the results for like impact analysis, or if you have your own global climate model and you want to run similar simulations, please get in touch. There are many ways in which you can do it very wrong, and so we made all the mistakes, so we can tell you all about them. So, thank you.
Okay, great. So yeah, we want to open it up for any questions or comments from the audience, and so either directed to Sarah or Mike, Matthew, or yeah, and
quick question, Oh, sure. My name is Nico. I work in policy at Silver Lining, and I'm curious about how at this conference I've heard people express, sort of sometimes even equate SRM with SAI, or just express a lot more confidence in SAI, without, and especially about the development pathway, for example. What makes you take MCB so seriously?
So I would say that I'd take MCB seriously because we're already doing it. And I don't mean we're doing MCB as a climate intervention. I mean that human emissions of particles to the atmosphere, I mean, I showed you the ship tracks example, but that's actually a really small part of the forcing that we're producing. Particulate emissions right now that we're adding to the atmosphere from burning things are making clouds more reflective around the globe in a way that's offsetting about a quarter of climate warming from greenhouse gases. So we're already inadvertently doing marine cloud brightening and cooling climate that way. The ship tracks example shows a very clear, I mean, that's the most direct analog where you can see that ships, without trying to, are going underneath these clouds, adding small particles to them, and not always, to be clear, but often making the clouds more reflective. So we just have these like direct, observable ways in which marine cloud brightening can be very powerful cooling climate mechanism.
I'll just add that I think the aerosol cloud interactions are the largest source of uncertainty for future climate projections. So like figuring this out will help us to narrow down aerosol cloud interactions and really hone down on the uncertainty for future climate.
Hi both, thank you so much for your talks. I'm Madeleine Luck from Cogita Climate Foundation. And something that people seem to talk a lot about is obviously the ship tracks that are already contributing to marine cloud brightening. And I was just wondering, and it probably belies the fact that I don't do as much reading as I probably should, but why do we put radiative forcing in boxes as opposed to kind of making it run along the shipping routes that already exist if we're talking about putting monitoring and aerosol emissions capabilities on ships? And secondary to that, obviously there's like an order of magnitude between some of these models and how much aerosol you'd have to kind of emit to get those radiative forcings. What does that actually look like if you put those aerosol nozzles on the ships? Like how many are we talking? Do we have any idea of that?
Yeah, I'll take the last part. I mean, you could effectively put a spray system. So I think you're aware that these ship track images are actually now a bit old because in 2020 they reduced the emissions from ships, basically the sulfur emissions from ships by about 80%, and so the amount of particles they're emitting is a lot less, and so that a lot of that forcing has gone away. You could put a spray system on each of those ships to basically make those ship tracks again but with sea salt. I'm not sure I totally understand the first part of your question. Are you talking about in the models? Why don't we? Oh. Well, if you were to do, I mean, so to be clear, ship tracks, they think that they've, like I said, there's been an 80% forcing emission reduction from ships. The forcing that's resulted is maybe 0.05 to 0.1 watts per meter squared. So you wouldn't, if you were to try and do marine cloud brightening at a scale that would substantially cool climate, you wouldn't be doing it just in shipping routes. You could probably actually, if you put spray systems on ships that were optimized for MCB, which obviously is ship emissions are good at it but aren't optimized for it, you could probably not just reproduce the ship forcing but maybe double it or something out of it. That's a very hand-waving, don't quote me on that number. But still to do it at a scale where you're talking about offsetting, 0.25 or 0.5 degrees CO forming, you'd be wanting to do it, it would need to be done over a much broader region, so you would be doing it with multiple plumes with the idea that they wouldn't produce those bright streaks, but that you'd produce a more diffuse. Yes, please.
I will say, so I guess historic ship tracks are very concentrated in the northern hemisphere, right? Mainly in the North Pacific and North Atlantic. And what we find from global climate modeling is that if we're just cooling in the northern hemisphere, you will tend to shift around precipitation, especially reducing precipitation in many northern hemisphere monsoon regions. And so what we're finding is that we need to distribute more equally, or more in a greater regions, especially in the southern hemisphere, to avoid those kinds of impacts.
Is this on? Yep. Thanks, both of you, for your talks. My question's mostly for you, Matt. That's a really interesting result that you can sort of do cloud brightening in a certain way and get a fairly even forcing, similar to SAI. But you know, Sarah showed us models at the beginning, right, where different models give very different results. So I was just wondering, have you done any sort of intercomparison on that result yet between different models, or is it at this stage sort of a one-off?
Yeah, so we did it in 2 models. So Haruki did it in the CESM2, and I ran it in the UKSM. So I showed actually from the results from 2 models, and they're quite similar across the 2 models. So the similarity, sorry, between SAI and MCB is true for both of the models that we did it for.
Okay.
But we're trying to get, obviously, more models to come on board so we can, be more confident, I guess.
And just to be clear, the way that the global model runs that he showed are set up is the first thing you do is in your model figure out what you would need to emit for sea salt to get a certain forcing basically in each region, so it bypasses effectively the stuff that the global models don't do well that I was talking about. Does that make sense?
Yeah, okay. So, yeah, I wondered about that. So, because you are implicitly forcing them with aerosols, though, right? You're not imposing a cloud droplet number forcing.
That's right, yeah. You're
but
increasing
you're tweaking the aerosol forcing until you get what you want.
Yes, basically.
Yeah. Okay, oh, well, fair enough.
Hi there, can you hear me? Yeah, excellent. My name is Adam Veltz. I'm a Cape Town-based environmental journalist. I work mostly for publications in the United States. I have deeply stupid questions because I'm very, very new to this, but so you folks might not even be the right people to answer them, and that's fine. I'm just trying to get a sense of the practicality of all of this. From what I'm understanding, the sprayers have not yet been optimized. We haven't even built a sort of really good sprayer yet. I'm also trying to get a sense, like, from your modeling, I'm talking on like a regional scale where this might be a little more useful maybe than at a global scale. We often hear this example of the Great Barrier Reef. In realistic terms, how many ships do we need to make any kind of meaningful difference to bleaching on the Barrier Reef? I mean, are we talking 3 ships, 10,000 ships? You know, again, I'm just trying to get a sense of the, are we, I'm not trying to be rude, but is this really something that might happen one day and be of any use at all? Because at the moment, as a skeptical newcomer, I'm not seeing it.
So I would actually say that both our group and Daniel's group, Great Barrier Reef, right there, you should talk to him, have made spray systems that can generate the right size of aerosol. Neither of them are scaled to producing a large cloud perturbation, but I mean, there's nothing in the way of simply taking what we have and, well, you could build 5 of them and have them in one base, effectively one location, and produce a big enough perturbation. But it's not. I think it's you know, the engineering side is doable. I can't answer the question about how many ships you'd need to cool the Great Barrier Reef. There is an issue with the Great Barrier Reef with cloud cover, but Daniel would be the one to answer that.
So, look, I'm not sure I completely agree about the tech. Like, back of the envelope, I think we need about a 30 times improvement in the production rate of aerosol per unit energy before sort of implementation type sprayers are viable, right? So there's a bit of a, you know, sort of like a technological jump that still has to happen. I mean, what we have now is really a outdoor experimental apparatus, right, to start to look at how the clouds respond. But if you did get that sort of 30 times increase, I mean, we're doing a bit of modelling work for the Australian government at the moment, looking at what's a minimum viable implementation over the reef, and it's probably, what's about 13% of the Great Barrier Reef. You only get sort of 60% of the cooling that you would get in that region if you'd done the whole reef, but it's sort of a pretty good trade-off, you know, getting 2/3 the cooling for only doing 13% of the area sort of thing. And that would be, if you just did it with ships or like sort of stationary barges, probably 50 to 100. So it's substantial. But there's a coverage problem over the Great Barrier Reef that is a little bit different than if you're trying to do something with a global forcing, because for each station it's only got a limited amount of kilometres for the plume to spread and mix and influence clouds, right? Whereas if you're doing it out in the middle of the Atlantic or the Pacific, you can, those aerosols have a much longer fetch to create an impact.
Hi, thanks for the talk. Just a very sort of simple, easily answerable question. Just to make sense of the number of teragrams that you put into your model, from someone that's trying to actually make these, the droplets as well. What size are you using? Because you can easily have a magnitude change in the teragrams if you don't say what size they are.
Yeah, so that's a good point, because actually we optimize the size for each model. And so CESM2 and E3SM use, is it 80 nanometer diameter, Haruki? Yeah. And it's about 170 nanometers diameter for UKSM. So a lot of the mass difference is actually because we're using much larger aerosol in UKSM. Yeah.
But this goes back to the talk I gave, which I think you missed at the beginning, which you cannot use these models to infer how much salt you'd be emitting in order to produce a forcing. Because I could give a long technical explanation, but they can't represent the sizes that are optimized for MCB. The activation schemes in them right now are not built for working with the sizes that are optimized for MCB, so you're forced to use larger sizes to get the forcing.
Right.
This is the whole issue, that these models don't do the aerosol cloud interactions accurately, so you shouldn't use them that way.
Yeah.
But you should use them the way that they are using them, which is how does the climate respond?
Yeah. Okay.
Make sense?
Yeah. I was just referring to the teragram.
Right,
the
but I
plot
would
there,
not.
but yeah.
I think that highlights an issue with the models. It doesn't highlight what you would need
Right.
to do MCB.
We'll have this gentleman in brown jacket and then to the back, and then by the order.
This could be another stupid question. You mentioned that marine cloud brightening doesn't create cloud, but rather it brightens a cloud in certain type of clouds. I'm assuming they're low altitude clouds. But those clouds are also disappearing, right? That's the NASA picture shows that they are disappearing. So do we have enough clouds to maintain the temperature? Where do we find those clouds? And my third question is that, does it have to be salt water to do the cooling? Can you do that river water? So let's say I want to cool my city that is warming, getting very hot. I want to cool it. Is it possible to do that with river water, maybe algae or something that can create the cloud condensation nuclei?
So there is sufficient cloud cover. The ocean has got a lot of low clouds over it. There's a pretty large fraction of the ocean is covered with these low marine clouds. So there is sufficient cloud cover available to be brightened. The brightening effect is occurring through the particles being added to the clouds. We're not cooling the clouds by adding water. So it's by adding particles. We're using sea salt particles because they're available over the ocean really easily. They're natural, they're non-toxic, they're hygroscopic. In other words, they act as effective cloud condensation nuclei. You could do it with other particles. You see that in ship tracks. So we could go out and burn things and use combustion instead, but that would be creating pollution. And you'd have to bring a lot of stuff over the ocean to burn or to add to the clouds. In terms of doing it like over a city, like you're talking about, we're not talking about misting water to produce cooling. We're talking about adding particles to clouds and making the clouds more reflective. So I think you would need to have, you would need to basically be targeting clouds over the ocean that are amenable to brightening. And if that cools your city in doing that, then that's great. But you're not going to do this over a city. Does that make sense?
Hi, thanks for the talk. It's really interesting. Henry, Matt, I wanted to ask about the timing that you mentioned, and in relation to the shipping regulation controversy, which has been quite lively debate that I've followed as a non-STEM scientist. I've tried to follow it at least. You seem to suggest that it would take like up to 15 years for the effect to happen, and does that somehow complicate or contradict the thesis that the shipping regulation caused the recent surge in warming, or how
Yeah,
does
that's
that
a
work?
great question. So first, I'm only speculating on just doing a quick analysis of the simulations that we've done. But also, you can look at the graph, and basically the temperature goes down very fast for the first 2 or 3 years. So obviously, IMO is a warming signal, so you can imagine the warming signal going very fast for the first 2 or 3 years. So I don't think that that would affect like the work that's been done on explaining 2023, 2024 warmth with at least partly due to IMO. But yeah.
Well, actually, I would say that the implication is the opposite of what you're inferring, and it's that probably all the warming due to IMO hasn't been realized, has not yet been realized, because the time scale for the full response is longer.
Yeah, there's more to
Makes
come,
sense?
basically.
There's more to come.
Yeah.
So that's actually the reason for the longer temperature response in the mid-latitude MCB simulations is something that I'm looking at right now. And my theory that I'm hoping to confirm in the near future as to what's happening is not that there's no temperature response right away, but the reason the temperature response gets larger over time is because of sea surface temperature cloud cover feedbacks in response to the intervention. And so in the tropics that doesn't happen, as it happens much more quickly. And so basically 2 comments. The time scale of the responses of the climate response to IMO shipping regulations is going to depend significantly on where those aerosols are no longer being introduced. And my opinion is that if it's for changes in the tropics, it's going to be realized very quickly. And in the mid-latitudes or at the higher latitudes, it would happen more slowly. I can stop there. I'm still working on it. Thank you.
For actual nozzles we can deploy now, is directionality of net global temperature effect from deploying marine cloud brightening known? And if not, what do you need to get there?
What do you mean by directionality?
So for the mix of particles too large and actual particles in the target range, net global effect on temperature for deployment.
You mean if we use the existing nozzles, would we produce a warming versus a cooling?
Exactly.
From the numbers that I've seen from yours, not if you intelligently used it. I mean, you're not going to always, with marine cloud brightening, you'll want to understand the existing conditions. What are the clouds? What's the atmospheric conditions? And then make decisions about spraying or not spraying. But I think your system and the one that we have both are producing aerosols in the size that's going to produce brightening under the conditions in which you would. Yeah. Yeah. Yeah, if you had the if you had particles of the wrong size to clouds, you can make them, which is what cloud seeding is for weather modification. You add large particles to clouds, you make them precipitate, the cloud goes away, you've now decreased reflection of sunlight by clouds. But yeah, we're not in that realm.
Sorry, can I go back to WMO? And sorry, but it seems you've said that most shipping is concentrated in the north. If you do this kind of intervention, it could have an effect on monsoon distribution if it's concentrated in the north. So this would seem to be of material interest to organizations like the WMO, who spend an awful lot of time both with national meteorological organizations and themselves trying to get better at predicting global weather. And so to what extent is this community intersecting with that meteorological community? Because you've got a real-time experiment that's just happened, right? That could give you some observable data rather than model data, which I imagine would be quite valuable.
Yeah, so this, I would say this is a significant difference between the MCB research community and the SAI research community, is the vast majority of work that's going on in assessing marine cloud brightening is like happening through research in groups that for decades have been studying how clouds evolve, how they form, how they respond to aerosols, working on ship tracks, working on, yeah, exactly what you're talking about. It's most of our work is going on within that scientific community because it's about understanding these aerosol cloud interactions. So there's already enormous overlap. So yeah.
Sorry, just a follow up then. If that's true, then like where as a policymaker does that emerge out as a message? Like is WMO's State of the Climate report looking at the things we've just done, these big global experiments of taking particles in and out of ship exhaust fumes? Like that would seem to be something that needs to be surfaced, like not just in the academic world, but out into the real world. Sorry,
Yeah,
not that you're not real.
Like,
but
I mean, I guess I feel like it has been, and it, you know, will be in through the like IPCC process. It's, I think it's, yeah, it's discussed at WMO. So I think it is being discussed and part of the conversation in those circles.
Yeah, I'll just add there's been like a flurry of papers on IMO and like global modeling of IMO impacts. So yeah, I think it will then make its way to the reports, various reports
Yeah.
that we're talking about.
I think it has been translated for policymakers. But if you think otherwise, let's talk.
Hello, thank you both for great talks. My question's for Matthew. I'm just curious, given the uncertainties in the aerosol cloud interactions that you've been talking about in the models, do you expect that your results would have been different if you had done something like prescribing CDNC instead?
That's a great question. I guess our approach was to optimize the sea salt aerosol emission to get a certain forcing in each of the boxes. So I guess if we did it through prescribing CDNC, you just do the right amount in order to get that given forcing that we're targeting. So I then don't expect the like global climate impacts to be that different.
Okay, sorry.
Okay, go for it.
Hi, I'm Graciela Raga from a scientist at the National University in Mexico City. I was fascinated by the very similar response that you got in the two models to the cooling, right? And I was wondering, I mean, all the mid-latitude regions are very large, right? And they have quite a latitudinal extent. So the ambient conditions of those clouds are changing, maybe large. I don't know, I haven't studied that, but maybe large. And we know that the conditions are important for the cloud field evolution. And you, Sarah, mentioned them as well. So the response seems to be similar in all regions and all seasons. Well, although you didn't go into very much, I'd be interested in looking at that. But so can you determine how the cloud fields themselves changed in those grid boxes, macroscopic characteristics? What happened when you changed the radiative forcing in the imposed compared to the base case scenarios, right? And how did the system respond? Did you get the cloud adjustment only with the radiative forcing imposed, or didn't? You know, those kinds of issues. I'd love to hear about those. Thanks.
Sorry, my answer is going to be annoying. It's the simulations have just been done, so it's really just hot off the press. And yes, all these questions are super important, but we just have more work to do. Sorry about that.
Sorry, yeah, if I could just ask another possibly really dumb question, but I know it's in the...
Stop saying that.
It's in the, yeah, but I mean, I'm not anything like an expert. I'm just kind of trying to think here. I know it's in the clean fuel era, but in the last couple of years since the whole Israel-Gaza thing blew up, global shipping traffic has changed radically. And I mean, I live here in Cape Town on the ocean, and there's just masses more ships coming past the Cape now than that used to go through the Suez Canal and the Gulf and so on. And I see it just with my own eyes. I can see the layer of pollution from these new ships. You know, this volume that we just didn't see before. You know, is there nothing to be learned from that? Looking at before and after, you know, and the change in and the possible effects of this pollution in different, radically different parts of the ocean.
Yeah, maybe, I guess I don't know enough about how big those changes are. A really
huge,
challenging thing with analyzing changes in clouds from the ship tracks, even with, you know, an 80% reduction through major shipping lanes, is clouds are really variable, right? There's a huge amount of variation just naturally in the clouds, in the atmosphere. And so trying to pull out the signal of where, you know, how much of a change has occurred because of a change in shipping emissions is really difficult. And I suspect that the changes you're talking about are at a scale that's much smaller even than that 80% reduction in emissions. It may be with enough time and statistics, if those changes were consistent, that you would have, you know, 5 years of data to contrast with another 5 years of data, and it would pop out. But I suspect that will be a pretty hard signal to pop out. So, yeah.
I think the IMO was, is it 8 teragrams of SO2 per year that has declined in 1 year? And we're still debating like how strong the forcing from that is, right?
Like the estimates span a pretty big range even now.
Okay, so going back to this MCB and ACI, the models, you found the results are very similar in terms of cooling and also the precipitation and other things. So given that results, why would one choose MCB over ACI? What are the pros and cons in this?
Answer that to me, okay. Yeah, I mean, well, so I think that's we're scientists, and maybe that's a question that's got so many considerations. I mean, you're talking about making decisions about its deployment, and I think there's just you know, everything from like which one do people find scarier for irrational or rational reasons, logistically, you know, which one's easier to do. I mean, people will argue that MCB is more reversible than SAI, and it is in the sense that when you add particles to the lower part of the atmosphere, they only last in the atmosphere for a few days. So you can turn on MCB and then turn it off, and 3 days later, 5 days later, a week later, for sure, all those particles are out of the atmosphere. But if you did either of them at a sustained enough level to actually cool climate, especially for a long time, you're going to change atmospheric temperatures, you're going to change sea surface temperatures, and then you're going to change circulation patterns in a way that will take a while to reverse. So if you do either one at a scale that's going to substantially cool climate, the reversibility time scale is probably the same or similar for both, even though the particles with SAI last in the atmosphere for 2 or 3 years.
So just to stop that, so you were saying that no, one of the considerations we had, I'm looking from the policymakers' perspective, right? That's what I'm looking at. So one thing is that, you know, we thought one of the consideration is that it will last longer. I mean, SAI, those particles will stay longer. In this case, if something goes wrong, I can, you know, stop it. So that consideration is not valid, you are saying, is it?
I would say that I would be careful with that consideration, because it depends on, if you're talking about wanting to do, if we ever got to the point of wanting to do like a large scale field experiment where you're actually doing something that kind of is close to deployment and do it briefly. With SAI, if you put a lot of particles up there, they're going to stay there for 2 or 3 years. And whatever effect that has will stick for a couple of years. With MCB, you could I don't know why this is probably totally irrational and wouldn't happen, but if you took 1,000 or 10,000 ships and had them all spray for a month or a year and then stopped, it would be more reversible than SAI. It would more quickly reverse. But if you're talking about at a deployment scale where you're cooling climate, no, I would say that it's not true. There's a false sense that MCB is, you turn it off and it stops, the effects stop. And if the effects reach the point of changing sea surface temperatures, which is kind of the goal with all of these things if you were to ever deployment, that the time scale of reversibility is, you know, something like 5 years, or if it's a lot of cooling over a large area, potentially longer.
Another consideration for the policymakers would be the cost or the difficulties. What do you, any thoughts on that?
I mean, if you were talking about trying to like go out and do something tomorrow, SAI, you know, David Keith and others have argued that you could do SAI at high latitudes only with existing aircraft, and that would be cheaper certainly than trying to like spin up enough ships to get that same amount of cooling out of MCB immediately. I don't think we know enough yet. If you're talking about true deployment, like, you know, to get a 0.5 degree C of cooling or something, I think we just don't know yet, because at that point you'd have to be developing high altitude aircraft. For SAI, you'd be developing ships. Potentially we'll find that you could do MCB without, in some locations, without developing ships, where you could have, you know, platforms, barges, or even I've thought about like you could site windmills that generate their own power, and because they could be in fixed locations. But these are just so speculative.
I think there could be models on that. Reflective has done models on SAI, how much it costs, how many planes, what kind of things that can be done. I don't know how accurate they are. I'm sure over time there will be higher accuracy over time. But similar things probably would be helpful if someone wants to choose one over the other.
Yeah, I just don't think we're at the point of wanting to choose to do any of them, not to mention one or the other. And I would also push back against the framing of one or the other. I think it's very possible, you know, with any of these approaches, any negative side effects increase the more you do. I'm not saying this is the answer, but it may be that that if SRM is used, that the sort of optimal thing to do will be a little bit of SAI and a little bit of MCB. But again, we just don't know enough yet. Right. Oh yeah. I think you're presenting a perfect argument in support of research, because it's pointing out that probably quite soon people are going to decide they want to use these things, no matter how much we know.
Hello. Hi, this is Jess from University of California, San Diego. I think your results were really interesting. I think probably the most striking thing to me was the seasonal results, actually, which I think you kind of went over kind of quickly. But at least when I saw the maps briefly, what struck out to me was the Northern Hemisphere summer. Yeah, JJA. I see a lot of warming over land, actually. And from kind of an impacts perspective, that might be seen as more of a failure than a success in terms of reaching some sort of temperature target, right? Because we live in seasons, we don't live an annual average. So I'm curious if you see similar patchworkiness in stratospheric aerosol injection results, or if this is still an indicator that we're getting this patchwork response from marine cloud brightening, it's maybe not as effective as stratospheric aerosol injection.
Yeah, great point. So this is very preliminary research, and also, so the maps are showing the temperature change relative to the target. And so if you're doing like a risk-risk analysis, obviously it'd be a lot cooler over land relative to SSP245 in that time period. But so yeah, it's relative to the target. Yeah, and I think we should do this kind of seasonal analysis both for the MCB and SAI simulations and compare. You're right. Yeah, maybe it's not as effective over land.
Thank you both. My name is Mike Farron from ARIA. I just wanted a strange question. I hope it's relevant. You have to put tens of thousands of ships additionally to those that are logistically used now for MCB, right, in order for it to work. Does anybody ever model the radiative forcing that comes from just using the ships.
You
along
mean
with
the
NCB.
energy use by the
energy
ships?
use, exactly, yeah.
Yeah, I mean, there's been enough back of the envelope calculations to see that there's sort of orders of magnitude of difference between the forcing that you get from the energy used by the ships versus the cooling forcing you would get from MCB if you're able to optimize it, which is an if still, yeah.
Hi. Before I ask my question, I just want to endorse what that gentleman was saying over there. It seems like a kind of no-brainer to use the opportunity that we've got at the moment with the changes to global shipping to try and see if we can get any background data, and maybe the Houthis could apply for a grant from Reflective or Outlier to fire a few more missiles to help perturb the signal a bit more. I wanted to talk about off-target effects. We're not talking about mixed phase cloud thinning or cirrus cloud thinning here, but that's very prone to off-target effects. If we don't have the right distribution of perturbing nuclei that are released, if we do it in the wrong clouds, it causes chaos and reverses the sign. And I'm very unconfident that we could ever do that reliably because we can't monitor the clouds accurately enough in real time, nor where our plumes will go, okay? Now, my question, and there is a question, is to what extent is MCB seen to be at risk of suffering the same effects? Could minor changes in our ability to direct MCB to get the droplets in the right place, to get the right size of droplets, could any small changes in those factors mean that we just either massively suppress what we are trying to achieve, maybe reducing the effect by an order of magnitude or so, or maybe even reverse the sign? Or is it just much less sensitive than cloud thinning to off-target effects?
I think mixed phase clouds and cirrus clouds are for all the complexity that I showed about low marine clouds, they're vastly simpler than mixed phase clouds or cirrus clouds. There's been discussion about if you add the wrong size particles or under the wrong conditions that you can produce the opposite of the effect you're hoping for. I think that we're quite confident at this point that we're understand the conditions well enough that it would be a very rare case where you would actually produce cloud, might call it cloud dimming. I think it's more a question of how effective will it be. I would disagree with this idea that that we don't even know where the plumes would go. I think we're pretty good at this point at weather forecasting in terms of like, air transport, air flows, and be able to forecast that. Is that
Sorry,
what you meant?
one of the principal concerns I've got is that we might initiate precipitation, dry out the clouds, and then you remove your downstream clouds. Are we confident that won't happen?
So the clouds, the low marine clouds that we're talking about, like stratocumulus clouds, tend to produce really light drizzle. We're not talking about like heavily precipitating clouds. You might shift slightly where precipitation occurs over the ocean, but it's not like cloud seeding for weather modification where you're going to be changing clouds that are like heavily precipitating clouds. So I don't want to undersell the amount of uncertainty and the potential for MCB, but I think we're also out of the realm, pretty safely out of the realm of the possibility of going out there to do it and inducing the opposite of the effect we were hoping for. It just may not be, it's how good will it be, how efficient will it be?
What do you need to get to where you can tell me to an order of magnitude per ton of particles deployed, you will achieve this temperature effect? To an order of magnitude? Or can you already do that?
To an order of magnitude, probably. I couldn't tell you the number off the top of my head, but I mean, it's about understanding the aerosol cloud interactions under different conditions, and then how often do those different conditions exist? So we're right now working on using those, a combination of observations and those high resolution models to analyze statistically how do clouds respond under different conditions, how much brightening do you get, and then how often do those conditions exist in different locations. There is the important point that Graciela brought up about that those conditions might change with changing climate. There's some interesting questions there to be had. And also whether you could actually maintain current cloud conditions through marine cloud brightening.
Hi, my name is Francisco. I'm from Chile. And when I see the question, the discussion question, is perfect because our team in this moment, we study the extreme weather events, and our study area is the Andes, from basically Ecuador to the end of the America. So the extent latitudinal is perfect to evaluate the impact of this SRM. So one question is what variables we need, something like that. So our neck is how represent the mountain Andes, because the topography is complex. So we need, in the downscaling, we need variables in different pressure levels. So my question is if your experiment has the variables we need, some like specific humidity, geopotential height.
Yeah, I was going to ask, like, what variables do you need?
Hmm?
So I was going to ask, what variables do you need? So is that the variables you...
Perfect. So our objective is, in this moment, so is evaluate marine clouds brightening in our project. Perfect. That is all. So please keep the contact for
yes,
the
yes,
data.
Definitely.
Thank you.
That'd be great. Yeah, we can chat later. Yeah.
Are there any other questions from the audience? I think Francisco brought up a very good point about collaborations between people who are already running the models and people who want to start doing impact modeling or run more models. So I wanted to segue into this question, which is open to both our speakers and the audience. So marine cloud brightening is a small-scale intervention, like relatively compared to SAI, but it's going to eventually affect the entire globe with the global temperature target that we set. So how do you feel about it, and what do you think in terms of like your country or your region may be affected, even though if ever there is a deployment, the deployment might not be next to your country or region? Is it too long of a question?
Well, okay, maybe I can rephrase it, or I guess as modelers, our sort of first impulse is to try to do like an ideal MCB case, like we're trying to minimize the impacts relative to, relative to the historical climate. And so I guess one of the concerns is like, is that really the way that MCB will play out? Will it maybe be more regionally focused? And I guess if you are someone who's concerned about MCB impacts, you can analyze these, but are there different types of scenarios that you would be interested in studying instead? Would you be concerned about regional deployments?
I don't know much about this, but I do live in the southwestern US, and it's very dry there, and our precipitation is very sensitive to sea surface temperatures far away from us. And so I do have probably more concerns about MCB, honestly, than SAI, because I would like water where I live. So that's just my kind of knee-jerk reaction to all this.
I mean, I'm cognizant, this is a little ironic, the for-profit balloon guy is saying this, but I'd like to politely, maybe consider lighting a fire under everyone's ass. Like, people are needlessly dying every moment that we don't deploy every measure on which we are sure of directionality. And, I think we need the clarity. You had two policymakers in this room asking, I'm not saying you have it in Like, we need some urgency with this research because we are geoengineering via our carbon emissions. We've been doing it for hundreds of years. Nobody cares that nature doesn't care that it wasn't our intent. So, yeah.
So I think the directionality, you're talking about, global annual average temperature. These are more even than we expected, but I think, these are the first, I would say, robust global model runs of MCB where I shouldn't say the first. We are in the very early days of doing global model runs of different implementations to MCB. And, it could be that these are wrong, or, I think that it's, we just don't know enough to say that it would be only a good thing to do this at this point. It's possible it could have very negative consequences in some regions still. So I just don't think we have the confidence to be making a decision to do this.
Yeah, I completely agree. And I was going to say, I don't want to overstate my confidence about the similarity between SAI and MCB. It's like literally a few plots that we've done, right? So we still have a lot of work to do, I think.
Yeah, just to reflect on that, kind of not what we know, we don't know. You have these 5 boxes, and as you say, you try to balance them with the mass load in the top and the bottom. But in the messy world of deployment, like, shouldn't you be modeling like really imbalanced releases? Because question: Are you seasonally deploying? Are you doing it throughout the year in an equal, like? There's probably a lot of complexity and variability in the deployment aspects, as well as the impacts that you're showing here, which would presumably change the model runs.
Agree, yeah. So we are doing it over the whole year, so there's no seasonality. There was a talk yesterday from Erin, who's just here, showing that the seasonality of MCB actually also matters a lot for the impacts. And as to the question of why we're doing it in a mass balanced way and not just like more in one hemisphere or the other, it's just that we know that's going to screw up the ITCZ. So like, we already know that's a bad scenario, so we're not
Same
doing
with
that.
SAI, as with SAI. I mean, if you did all the SAI in the Northern Hemisphere, it's the same rationale, basically. You're going to shift to ITCZ.
I wasn't really questioning your mass balance. That seems logical to me. But what I'm saying is that actually in deployment, it's likely to be not as smooth as you imagine, right? You're talking about the ocean. You're talking about, like, there isn't a benign God that's just going to go, oh, yeah, let's all
Well,
move
this
together.
goes back to my answer to Luke's question, is we just don't, these are early runs. There's just a lot more to do to understand how different deployments would play out, and what the pluses and minuses of all of those could be. And also, this is, like I said in my talk, the climate responses you're getting here are if you can do that amount of brightening in those boxes. But we're still doing the work to figure out how much brightening you could get in different conditions. So it's not for sure that you could even do this.
I think it's probably fair to say none, like maybe absolutely none.
None
of the
what?
sort of
Sorry.
modeling runs that have sort of been done and published so far on this actually really in a serious way take into account the engineering of deployment, right? So that's just a wide open gap that's not even being addressed yet, and it needs to be.
We're trying to do a lot of things in parallel because of the urgency of the problem, but that requires that we make we start with like a starting point in the global modeling where you're not being realistic. You're having to impose the amount of cloud brightening to try and understand what are the climate responses. At the same time, we're trying to understand, could we achieve that amount of brightening in the boxes? At the same time, we're trying to understand, what does the engineering look like to even accomplish this? Yeah. I totally agree that different scenarios need to be explored. They're just, we have limited compute power, we have limited, you know what I mean? So
Sorry, but then there is a question. If you have finite resources, how much more do you do of this, which is clearly slightly untethered from reality?
Well, not
versus
necessarily.
The bottom, well,
not necessarily
you kind of
any more
said
than
we don't
anything
know
else.
this, we don't know that. This is unsure. This is optimal. Like it feels like you're running ahead on the narrative without the observability or the grounding in the bottom-up assessments, right? Drawing a box on a map that's God knows how many kilometers wide by deep and saying we're going to deploy here, that gives a false sense of confidence to policymakers that this is even remotely possible, right? So I'm just counseling that, A, do more observations on what we've just done with the particulates coming from the ships, right? Firstly, ground that down.
To be clear, we are doing that.
Do the bottom up, right? But you haven't presented that here, right?
I know,
in this session.
Right.
Yeah.
Yeah.
Earlier today, or? Oh, okay. Well, we all missed it. But anyway, my point is perhaps you could integrate it more.
In reality, it is. It wasn't here today, but in reality, it is. There's work going on in all these places, and there have been runs done where it's not implementing it just in mid-latitudes, and we don't know how deployable it is. You know, like how much we could brighten clouds in any one given region necessarily. So the uncertainties that apply here, I think, are general to any deployment scenario you come up with.
Can I just add to that, though? I think it's an even bigger concern if we're looking at impacts and risks, right? Because if we're looking at impacts and risks of modeled scenarios that are completely and utterly unrealistic, and then that's getting into policy, that's a huge problem.
And there have been some extremely unrealistic MCB global model runs that have been done with very big headlines that have, I think, already pushed people in the way that they think about it, that just they're just not realistic. You know, making statements about the massive of sea salt emissions that would be needed to do MCB based on a global model, they're off by a factor of 10. So
we have 2 last questions, and then we'll have to end it because of time.
Okay, so my question is that, what makes MCB attractive, at least at this point, over SAI, is that a regional deployment, that, okay, my area is getting too hot, and whether I can cool this certain area. Was that the use case scenario and possible?
I guess the issue is that if you do enough cooling to have a meaningful impact on your area, you might also provoke some potentially negative remote impacts through teleconnections. So it's unclear that you can just say, oh, I just want to cool my area, and that's fine. Like, it might shift rainfall somewhere else, like further afield. So yeah, I guess it's not as simple as that. Do you have a different answer?
yeah, well, I mean, guess again, I wouldn't pose this as why is one preferable to the other. Yeah.
So are there research done on this area? For example, I find, let's say India, and I see certain parts of India gets very hot in certain time, can cross the wet bulb temperatures, and I want to cool that certain area. How would that play to the other areas? What impact that may happen? Would there be any impact, or?
Well, I think that's related to what she was talking about. I mean, so I guess 2 answers. I think that the stuff that Matthew was showing is, trying to look at how are different areas affected by, this implementation of marine cloud brightening versus a similar implementation of stratospheric aerosol injection. So you can look at that for your specific area. But again, I think what Matthew was saying, what we're not doing is saying, okay, let's use MCB just to cool India. Because if you did that, you'd have to implement it in a way that would be, you'd have a large implementation in a specific area just to optimize for India, and it will have effects elsewhere. I mean, you could do that model run, but you could do that model run for trying to cool any one specific area. There's sort of an infinite number of combinations there. Well, not infinite, but large.
We can talk offline on this.
I hope Walker Lee can re-ask this question better than I'm about to ask it. But as far as I understand, there's fundamentally 2 ways you can do MCB. You can either concentrate on areas that are quite small and very prone to modification and modify them very hard, or you can spend a lot more money and concentrate on a much broader array of areas that are much less sensitive, and you have to spend a lot more shifting. But the advantage of the second one, which might seem otherwise fairly obviously stupid, is that you're not you're spreading out the degree to which you're changing the temperature of individual little regions, so that you're changing a lot of areas a little bit rather than changing small areas a lot, which is much less destabilizing for the climate. Do we know whether going for the spready outy version of marine cloud brightening versus the efficient and concentrated version of marine cloud brightening is going to be the safest and best way to go? So Walker, you might want to re-ask this in language that other people understand, but I think you know what I'm talking about.
Yeah, do you want to answer?
I guess I have there's two answers, or there's two aspects to that. I guess the first is that, you know, as you introduce more aerosols into the clouds, you get less brightening per unit aerosol injected. And so, yeah, there is like a microphysical argument that if you emit over a larger area, you know, you have a little bit of aerosol in a larger area will give you more forcing than the same amount of aerosol in a smaller area, typically. And that's, so, you know, there is some use from a microphysical perspective to spread things out. And also, you know, the point of climate intervention is to get climate change in. So really the efficiency is not the primary goal. It's the getting the right climate response. And then I guess I'll finish off the third. Actually, in the climate models we look at, the mid-latitudes that we're looking at here are actually more sensitive than the subtropics. That has a little bit to do with some of the details of our implementation. And we are very much out of time. So if you have any other discussion, yeah, please come chat with Sarah and Matthew. Yeah.
And Haruki.
Haruki. Thank you.